right, Jocelyn, can you give me some numbers you can take the square root of? Yeah. What's the square root of 0? All right, that's our smallest one we can do. The square root of 0 is 0, so 0 is 5. Cool, keep going. Cool, what's the square root of 16? Awesome, we're not going to be able to see that on the graph here, but yeah, if we went all the way out to 16, we'd get 4. What are some other perfect squares we could take the square root of? Yep, square root of 25 is 5. Again, we won't really see that on this graph because that'll be clear over here. So maybe, are there any other smaller perfect squares? Yeah, what's the square root of 9? That's one we'll see right here. Square root of 9 is 3. Cool, guys, give me a couple more. Well, I think there's only just one more, right? Oh, there's 2 more. What was that? Square root of 4 is what? And last one. Square root of 1 is awesome. So on our graph, we're really only going to see like these smaller ones. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. But it's good to know the other ones as well, right? Okay, that's the graph. Now, how is this graph different from all the graphs we've seen up to this point? Let's start by looking at the domain. Is the domain all real numbers? How come? On the other ones, it was all real numbers. What's different about this one? Well, what are we doing with those negatives, right? We're trying to take the square root of them. Can we take square root of negatives? No. So where will our domain actually start out? Can we include 0? Because what is the square root of 0? 0. All right. Great. So our domain, this is our first one we've seen where the domain is not all real numbers. Okay, what about the range? What is that going to be? Also 0 to infinity. All right, is this symmetric at all? No, because we'd say, is it doing the same thing on both sides? There is no other side, right? So yeah, no symmetry there. All right, Mikkel, what about increasing or decreasing? What is this one doing?
It's increasing from 0 to infinity, but it doesn't decrease.
Awesome, thank you. Are there any asymptotes here, guys? Nope. Is this, let's go to extrema. Ofa, what does this have as far as, does it have a min or a max? What is it, where is the maximum at? Well, so this is actually just going to get bigger and bigger and bigger and bigger. So anytime we identify a point and say that's the biggest, we can always look to the right and see it bigger. But is it ever going to get smaller than that point? So then we don't have a max, what we have instead is a minimum. And is this a local or an absolute minimum? It's going to be absolute because it is the lowest of all those points on this graph. So we have an absolute minimum at 0, 0. Okay, Peyton, is this bounded? If so, which one is it? Nice job. I could draw a line below it, so it is bounded below. All right. Now, as far as being continuous or not, that's not referring to where is it defined. Can I draw this without lifting up my pen? Yep, so this is not discontinuous, okay? As far as end behavior, does it have a left end? Just kind of stops, right? So we're just going to look at the right end. The limit of f of x as x approaches positive infinity. What's it doing on the right side, guys? Going up towards infinity. Okay, so how many graphs have we done so far? Is that 4 or is that 6? 5? Okay, let's do one more and then we'll take a break, okay? But first, let me quiz you. So warm up your hands because you're going to show me with your hands. Show me x. What does x look like? Identity function. It's just like this, right? Show me x squared. X squared is this one. Good job. Show me x cubed. We're just going to change that to s squared, right? Cool. Show me absolute value. Good. And then show me square root. Square root is just boom, kind of like that. Cool. Okay. The next one we're going to do here is called the cube root. Okay, awesome. So if square root, let's jump over to this. If square root was saying what number multiplies by itself to give you a number, what would cube root be? Say that a little louder, Adam. There you go. Let's just take this same thing here, but apply it to cubes, okay? When I was in 6th grade, it was a very important thing that happened, and it was that the Nintendo 64 came out, and it was amazing. Because before that point, when you would play Mario, all the games were in 2 dimensions. You could only go up, down, left, right. But then when you played Mario 64, guess what you could do? Have you played Mario 64? Shame. You should go play it. It's amazing. But guess what? You could go anywhere you wanted. It opened that 3rd dimension, so you could go anywhere. So now, let's look at this. If I'm going to, instead of squaring 5, let's say I cube it. What does that mean? 3 times. So instead of building a square, what are we going to build? How good of artists are you? Does that look like a cube? Sure. How would you find the volume of this cube? Length times width times height. You times it by itself 3 times, and I get 125. So to cube it, square a number is you times it by itself twice. Cube is 3 times. What's the opposite of cubing a number? The opposite of a square is a square root. What's the opposite of a cube? Thanks, class. All right, here we go. Let's draw a picture here. Not great, but whatever. Let's say this cube had a volume of 64. All the side lengths are the same. What number multiplies by itself 3 times to give you 64? And the answer is not 8. It is what? 4, because 4 times 4 is 16. 16 times 4 is 64. So the cube root of 64 is 4. Does that make sense, the difference between squares, square roots, cube, and cube roots? You kind of have to have this thing down. So it's hard for me to tell when you're wearing masks if it makes sense or not. So I hope it makes sense. Guys, just shout it out to me. What are some numbers that we can take the cube root of? Okay, cool. I heard 1 to start off. What is the cube root of 1? 1. Okay, give me another one. What's the cube root of 0? Awesome. What else? What is the cube root of 8? 2 times 2 times 2 is 8, so there we go. And we could keep going, and I think the next one is actually 27, but that's going to be off our graph. Now, are we done?
No.
Why not? Can you take a cube root of a negative?
Yeah.
Let's think about it. Let's look at the cube root of negative 8. What number multiplies by itself 3 times to give you negative 8? If I do negative 2 times negative 2, what does that give you?
4.
And what's 4 times negative 2? Oh, so since our index here is odd, negatives are okay. Notice when we were talking about domain, we said we can't take the square root of a negative, but did we say anything about cube roots? Cube roots are fine. It's just the even roots that we have problems with. So what's the cube root of negative 1? It's negative 1 still, so this is actually going to jump down here to the negative. What's the cube root of negative 8? So when we looked at x cubed, we had the s curve. And this makes that same kind of s curve, but it's kind of flipped the other way. Instead of going up and down, it's going left and right. Now it is still going to keep going up forever and down forever, but that's your general shape. So show me with your hands real quick. What does x cubed look like? X cubed is this guy. So what is cube root of x? There you go. You're going to make that switch like that from whoop to kind of fancy stuff there. Okay. Let's just get through this super fast. So first off, the equation here was cube root of x. It looks like that. Brinley, what is the domain going to be here? While you're thinking about that, I'm going to tell Brandon to do the range. We're going to then have symmetry, which is going to Lashea. Increasing, decreasing is going to Brenda. End behavior is going to Micah. And then whatever's left, I'm going to give to Adam. All right. Brinley, domain. Awesome, all real numbers. Thank you. Brandon, range. Yep. All right, Lashea, is this symmetric? What kind? Is this even, odd, or neither? It is odd. If I were to trace this and flip it over and land on itself, good job. This is odd. Awesome. Okay, so Brenda, is this increasing, decreasing, or constant?
Isn't it both? Because it's decreasing from the left side.
So this is, if I start in the middle and look right here, I could say, oh, it's increasing here, decreasing there. That's a common mistake because we're going to start over here. So if I'm looking from left to right, what's going on here?
It's increasing.
There you go, the whole time going up. So that means it's never decreasing. Micah, what about, what did I say you're doing? End behavior, what is it doing on the left? Yep, what about on the right side? Alright, so I'm going to write it out all fancy. Because you guys will see this a lot when you're in calculus, so good to see that there. Alright, Adam, are there any asymptotes? Any extrema? Is it bounded? Is it discontinuous anywhere? Alright. Is that the only thing you know how to say is no? No. Alright. Okay, there we go. We are going to take a little break here, and we'll come back and do the other 6, okay?